Hi everyone, in this lesson we are going to look at some circle proofs. As you can imagine, circle proof can become quite complicated, and case in point, proving the inscribed angles conjecture, that is, the inscribed angle is half the measure of the intercepted arc, actually requires something called cases, where we look at three different ways the entire proof can go. We aren't going to do something that complicated. We are just going to look at two proofs that also reinforce earlier conjectures that we've learned, including our parallel line conjecture and, of course, our triangle congruence shortcuts. Again, we just want to kind of dip our toes into this, and this also just continues to reinforce the just kind of the rhythm of a proof, the notation, the format, and just like that whole experience. So we're going to just start with a warm-up using our previous conjectures to just remind ourselves of what sort of features we've looked at with circles. So our first thing is we are going to find the measure of arc AD, and arc AD is the intercepted arc of angle ABD, and if angle ABD is 70, then the arc is double that. The measure of angle D can be found by using our triangle sum conjecture. So we have 80, 70, so that gives us 150. So angle D is 30 degrees. That's then going to help us find the measure of arc AB, which is the intercepted arc of angle ADB, or angle D. And so that would be double that. So that would be 60. And then finally, to get the measure of arc DAB, which is this full arc here, we would add those two together, and so that's 200 degrees. We could have also looked at arc DB and noticed that if angle A is 80 degrees, then that would be 160, and note that 140 plus 60 plus 160 is 360, and so again, those just reinforce all of the different ways you can approach a problem. So for this first proof, we are going to prove that if we have parallel lines, okay, one of them a radius, one of them a chord, we are going to show that we have arc DE is congruent to arc BE. Okay, so this is just kind of an interesting setup, and again, we're going to use a lot of other previous conjectures to kind of prove this. As with any proof, we start off with our given statements. I'm going to do a two-column here. If you want to transfer this to a paragraph or a flowchart proof, please feel free. You can use any proof method. So I'm going to have my statements and my reasons. All right. So I'm going to start with circle O with diameter AB. And that is given. And I'm going to say that OE, segment OE, is parallel to segment AD. So to show that arc DE is congruent to arc BE, we have a couple options, right? We know that if we have congruent chords, then we have congruent arcs, but I don't see chords DE and chords EB here. So then my second option would be the idea of looking at the central angles. So I have angle DOE, which is right here, and then I have another central angle EOB. So if I can show those angles are congruent, then I can show those arcs are congruent. So my want to show here is I want to show angle DOE is congruent to angle EOB. And if I can do that, then I can use the definition of arc measure to show that the arcs are congruent. So that's kind of where I'm going to go. Okay. The next thing I do when I look at a proof is I ask myself, why am I given the given? What does the given help me accomplish, or why is it there? And my given is that I have a set of parallel lines. And anytime I see parallel lines, you know what I'm looking for: alternate interior angles. So where are my alternate interior angles? I'm going to try to find that Z. So I have angle ADO and angle DOE. Okay, so my third step is going to be angle ADO is congruent to angle DOE. And why is that? That's alternate interior angle conjecture, or you could say parallel line conjecture. So why is this helpful? Okay, let's look at a couple things. We have those two angles are congruent. Do we have any other congruent angles? Why, yes, we do. We know that this triangle is isosceles. Why do we know that this is isosceles? Well, this is a radius and this is a radius, and all radii are congruent. And so that's the next step I'm going to take. I'm going to say that DO is congruent to AO, and that rationale is just all radii are congruent. Which leads me to conclude that triangle DAO is isosceles. And that is definition of isosceles. And because I have an isosceles triangle, we learned in chapter 4 that the base angles are congruent. So then I'm going to say angle DAO is congruent to angle, so DAO is congruent to angle ADO. And that is the isosceles triangle conjecture. Or you could say the base angles are congruent in an isosceles triangle. Okay, here we go. All right, we're doing great. All right, so what else do we know about parallel lines? Well, parallel lines produce our alternate interior angles that are congruent, but they also produce corresponding angles that are congruent. So I want you to think about this. I'm going to extend this a little bit, extend these parallel lines. And now I want us to consider this segment, segment AB, as the transversal rather than segment DO, all right? And what you're going to notice is angle DAO and angle EOB, those are corresponding angles, okay? So that's going to be step 7. Angle DAO is congruent to angle EOB, and that is corresponding angles conjecture. All right, can you see how we're almost there? So what we have, again, if I just kind of make some erasings here, we have these two angles congruent, the orange angles. We have the green angle congruent to the other orange angle, and then we have the green angle congruent to the blue angle. And so putting this all together, everybody's congruent to each other. That's called the transitive property. So how we're going to write this is we're going to say that angle ADO is congruent to angle DAO, which is congruent to angle EOB. And actually, sorry, I should have started with angle DOE, should have been the beginning part of the angle. Okay. So angle DOE is congruent to angle ADO, who's congruent to angle DAO, who's congruent to angle EOB. Now, I know that was a lot with all of the, naming all the 3 vertices. And that is the transitive property. And we finished what we wanted to. That was our want to show. Okay, that was our want to show. And so now, because we have the 2 angles that are congruent, angle DOE and angle EOB, by transitive property, we can conclude that arc DE is congruent to arc EB. And we're going to call that definition of arc measure. Awesome. And there we go. So of course, this was definitely more involved than some of the other proofs that we have been doing, but this is just what I like about this is it really brings in a lot of content that we've already studied and just shows you how everything in geometry builds and is connected. Okay, so we have another example here. This is one that we learned this conjecture in section 9.3. the arcs by parallel lines conjecture. So what we want to show here, what we want to prove, is that when we have parallel lines, we have these intercepted arcs that are congruent. Okay, let's set up. Again, I'm going to set up a 2-column proof, but you can go ahead and do whatever method works for you. Once again, we start with our given. So we'll say circle O with chord BD. And line AB parallel to line CD, okay? Again, we have parallel lines. We are always thinking about alternate interior, corresponding, etc. Okay, so you can see that they have conveniently labeled angle 1 and angle 2, and they make that Z. So we're going to just say angle 1 is congruent to angle 2, and that is by AIA, alternate interior angle conjecture. We cannot automatically say the arcs are congruent because of the angles are congruent, and this is because we have inscribed angles here. We don't have central angles. In the first example, we could automatically make that connection because the inscribed angle and the central angle have the same measure, and so that's a connection that we can make, but we can't do that here. So here's what we do. We are going to say that the measure of angle 1 equals twice the measure, sorry, half the measure of arc AD, and the measure of angle 2 is half the measure of arc BC. And that is our inscribed angle conjecture. This is helpful because remember, we already said that angle 1 was congruent to angle 2, and now by substitution, we can set 1/2 measure of arc AD equal to 1/2 measure of arc BC, and that's by substitution. And now if we have half of the measure of arc AD equal to half the measure of arc BC, what is that telling us? Well, that is telling us that those arcs are congruent. You could, if you want to, do an additional step and say their measures are congruent by multiplying both sides by 2, but I think we can just go ahead and conclude. Again, what happens is when we go from a measure to a congruence, or from a congruence to a measure, that is usually called the definition of congruence. Because if some things are congruent, it means their measures are equal. And I'm just double checking that this is what we wanted to show. Yeah, I mean, I didn't phrase it as DA. I did AD, but that is the end of our proof. So great job here. Again, these aren't going to be on the final exam, but I wanted you to take notes and I wanted you to go through this lesson just so that we can get more practice with proof and just see the connections of everything we've been doing. So great job, everybody.